Welcome back, students, to another episode of Notes for Class. Today's notes, we're going to be looking at section 15.5, the Mathematics of Finance. So we're going to start by talking about three different types of interest accumulation. So when we talk about interest, we're talking about supposing that you invested some money in the bank, and as a payment for keeping your money with the bank pays interest. So it pays you a small percentage of the money that you've left with the bank. And there is several different types or ways that interest is computed. So the first way is what's called simple interest. So our formula for simple interest is given here, where I is the interest gain, PV is the present value or original amount that we've invested, R is the annual interest rate per year that's written as a percentage, N is the number of years, and because we've written the interest rate as a percentage, it needs to be divided by 100, so that's what the dividing by 100 is going on there. So let's look at an example of kind of getting comfortable using this. So it says you invest $2,000 at 6% interest. How much money do you have in the account at the end of 3 years? Well, we're looking for how much interest we've gained. So I is what we're going to be looking for. The present value is $2,000. That's what we've invested. R is 6%, or just 6. N is the number of years that we've invested, so that's 3. So when I type this into my calculator, I get $360. But it asks for here the total money do you have in the account? So remember that total money is going to be the initial amount plus the interest. Let's write that as I. So here we have 2,000 plus the 300, or $2,360. So simple interest is pretty straightforward. You gain interest based on your initial investment. Now, that's quite simple and really not how things work. Really what we should be gaining interest on is the amount that's in the account when the interest is paid. Now that sort of situation is called compound interest. So that we're earning interest on top of our new value of the account. So the formula for a compound interest is FV is equal to PV times 1 plus R over 100K to the Kn, where FV is the future value of the investment, PV is the present value, or sometimes in investments we call that initial investment the principal. R is the annual interest rate written as a percentage. K is the number of compounding periods per year, and N is the number of years. So let's look at our first example. Let's say we invest $2,000 at 6% interest, compounded annually. How much money do you have in the account after 3 years? And then how much did you gain in interest? So this is a compound interest problem, and I can tell that because the word compound is in the description. So if we use the compound interest formula, we have this. So if we want how much total money are we going to have in the account after 3 years, we're looking for the FV. The present value, the initial investment, is $2,000. The interest rate as a percentage is 6. And then K, what is K? Again, K is the number of compounding periods per year. Notice in here it says we're compounded annually. That tells us that K should be 1. And then for N, we know that this is 3 years. So 3 years. So when we type this into our calculator, out is going to spit $2,382.03. Notice that when there were more decimals than this, but I rounded this to 2 decimal places because the quantity that we're dealing with is money. In situations where we're dealing with money, we would want to round to the penny, so 2 decimal places. So that's how much total money we have. If I want the interest, remember interest is going to equal our future value minus our present value. So that's $2,382.03 minus 2,000. So $382.03 was how much we made in interest. Just take a quick pause here and compare this situation to the previous one. So in a simple interest situation, we made $360 in interest, where everything else was the same. The interest rate was the same, and the period of investment was the same, and the initial investment was the same. In the compound interest situation, we made an additional $22 and some change. That additional $22 came from the interest on the interest. So going from year 1 to year 2, we had then $2,120 in our account. So we earned interest on that instead of just $2,000. So that's why it's a little bit more. Okay. Let's look at the next example here. So it says, suppose Gina invests $800 in a 7% annual interest rate account. How much money will she have in her account after 5 years if interest is compounded? And then we have a bunch of different situations. First thing I'm going to note is that this is a compound interest situation. So my present value, or the future value, is what we're looking for, because it's asking how much money will we have in the account in the future. The present value is 800. R is 7. K, here we're compounded annually, so again K is 1. And it's 5 years later. So when I type that into my calculator, I get $1,122.04. Let's look at the next situation. So if we're compounded semi-annually, that means K is equal to 2. Again, because semi means 2. So when I do that and type that into my calculator, I get $1,128.48. Quarterly means K is equal to 4. So again, everything else stays the same except for that value for K. Remember, K happens in 2 places, so we've got to be careful. So when we do that, we get $1,128.48. $131.82. Not much different. Monthly, well, there's 12 months in the year. So again, everything else is staying the same. I'm just changing my value for K. Do that, I get $1,134.10. Weekly, well, there's 52 weeks in the year. I'm not sure if you remembered that or not. So here we have everything else stays the same except for our value for K, which is now 52. When I do that, I get $1,134.99. And our last one, daily, let's assume it's a non-leap year. So we'll do 365 days in a year. So everything else stays the same except for the value for K. And when we type this into our calculator, we get $1,135.22. So if we compare, look at the size of K here versus in the beginning, the size of K, big difference, right? 365 times bigger. But if we look at the actual future value we've earned, $1,122 versus $1,135. So it was like an extra 13 bucks with all those more compounds, and it didn't make that much of a difference. So just kind of keep that in mind. Now let's do a couple more examples using this model. So it says Maria has $1,000 and places it in a savings account with 6% annual interest compounded monthly. How long will it take before Maria has $4,000? Notice this question is asking how long, and we know it's a compound interest formula. So which one of our compound interest quantities are we looking for if we're asking to solve a how long question? Let's make this a different color, huh? That's right. We're solving for n, the number of years. Okay. So let's fill in then our values. It says we have $1,000, so that's going to be our present value. And we get 6% interest compounded monthly, so K is 12. N is what we're solving for, and we want to know what value of n is going to give us $4,000, so that's our future value. So there's that. So this is just solving an exponential equation. We just got done doing this in the previous section. So the first thing that we need to do is get the exponential part by itself. So this is the exponential part. So what we need to do is get rid of that 1,000. So to get rid of that, we'll divide both sides by 1,000 because the 1,000 is being multiplied to that exponential piece. So 4 is equal to 1 plus 1 over, and I'm going to just multiply the 12 and 100 together. So 1 plus 6 over 1,200. So now we have to get rid of this exponent base. What's the best way to do that? Well, we know to cancel an exponent base, we can use a logarithm with the same base. So what I'm going to do to both sides is log base And I could write or type in this number into my calculator to get an actual value, but it doesn't really matter. So I'm just going to write it this way. Because my calculator can handle this. So those parts cancel. I'm left with 12n. And over here I have log base 1 plus 6 over 1200 of 4. And I need to now get the n by itself, so I'll just divide by 12. I'm going to write it as like multiplying by 1 over 12 though, because there's kind of a lot of stuff going on over here, and I think it just makes it look a little bit neater if I write it this way. So when I type this into my calculator, I'll actually show it this time because we're going to use that log base command, and I just want to remind you where we find that. So I'm going to do 1 over 12 times, and then I'm going to press the math button, go down to the bottom till I find the log base command, and now I'm going to just write 1 plus 6 divided by 1200 in the base of that logarithm, exactly as it's written there. So now you see why I didn't bother to convert it to a decimal, because the calculator can handle that for me. And it's just less writing to do it that way. So let's say is about 23.16 years is my value for it. Okay, one more example using compound interest. And we'll move on to the next topic. Gwen has 600 to place into a savings account. What annual interest rate would she need compounded weekly? So we know we're going to be using compound interest. And we know here that K is 52. If she wants to have exactly $1,500 in 10 years. So here I can say that n equals 10, and my future value is 1,500. So if we start writing this out, 1,500 equals 600 times 1 plus r, that's what we're solving for, over 100 times 52 to the 52 times 10. Okay, so the first thing I need to do is get rid of this 600. So just like we did before, we'll divide both sides by 600. So when I do that, I get 2.5. And again, I'm going to go ahead and multiply this and just make that 5,200, make that 520. So now, to get at that r, we have to cancel out this exponent. So what cancels out an exponent? Well, a radical. So which radical should I use in this case? The 520th root. So that's what I'm going to do to both sides. And again, I could get a decimal for the 520th root of 2.5, but I don't really care. The calculator will handle that in a moment. So now I'm here. So to get the r by itself, still what I'm trying to do is subtract 1 from both sides. And notice that I can't subtract that 1 from the stuff inside the radical. So I'm just going to write it here. And then my last step is to get rid of this 520 or 5,200. So to do that, I'm going to multiply both sides by 5,200. So remember, this is going to distribute here. Okay, and now this is calculator time. And again, I'll show typing this into our calculator so I can remind you how to get a 520th root. So negative 5,200 plus 5,200 times, and then I'm going to press the math button. I'm going to go down and choose this option 5, the xth root, because that's going to allow me to choose the root. I'm going to choose 520. So my value for r that I get is about 9.17%. And if you can find any investment that's paying you 9.7% per year, that is a fantastic investment. Put a bunch of money in that. That is excellent. That is quite excellent. Okay. Our last situation is continuously compounding interest. So this is a situation, a special situation for compound interest. In which our interest is not compounding every year. It's happening more than that, more than every month, more than every week, more than every day, more than every hour, more than every minute, more than every second. It's happening like every instant. In this situation, we're really having an infinite number of compound interests per year. So what happens then, if we take our compound interest formula and we just set everything to 1 other than k, and we look at what happens as k goes to infinity. That's what we're discussing when we say compounding every instant, is you have an infinite number of compounds per year. This quantity approaches some specific value. That specific value is an irrational number that's approximately 2.71828, and we call that number E. So the E in our compound interest formula is that. So this is why this number E is cropping up here. Okay, so our continuously compounding interest formula, FV equals PV times E to the Rn over 100. FV is the future value, PV is the present value, R is your interest rate as a decimal, and N is the number of years, and E is this constant. It's the same number. Remember, like in geometry, we used the symbol pi for 3.14 yada 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 for that irrational number. The same idea here with E. So Jack invests. Let's look at some examples here. Jack invests $800 into a savings account with 5% annual interest, compounded continuously. So when we see this word continuously and compounded, we know we're going to be using this new model. So if you don't see that word continuous, you'd use the other compound interest model. But as soon as you see continuous, We're going to be working with this model. And it says, how long will it take for Jack to have $500 in interest? So if the interest is equal to 500, I know that the future value is equal to the present value plus the interest. So that's going to be 800 is the present value plus 500 equals 1300. So that's my future value. It's my present value. And again, I didn't mention it, but we're looking for how long, so we're solving for n. So we have this. So we'll start by dividing both sides by 800 to isolate the exponential part. So that reduces down to 13 over 8. And 5 over 100 reduces down to 1 over 20. So we have that over 20. Now the next thing we need to do is cancel out this exponent base of e. To cancel out an exponent base, we need to use a logarithm with the same base. So in this case, we need to use log base e. And we have a special name for that. We call that the natural log, and we have a special symbol we use to abbreviate that. That is the symbol ln. So we'll take the natural log of both sides. And we know that the natural log will cancel out the exponent base of e. And then we just, to get the n by itself, multiply both sides by 20. And when we go to our calculator and type this in, we have about 9.71 years. Okay. Let's do one more and then move on to the next stuff. So the next example says you have find an account that has 6.5 annual interest compounded monthly. What would the equivalent interest rate for an account that is compounded annually? Okay. So notice here we have compounded monthly. And we have compounded annually. So in these situations, we're going to be using the same compound interest formula. And notice that the compounded monthly, K is 12, compounded annually, K is 1, and R is 6.5. So we know here that we're not given a value for future value, present value, or n. It turns out that none of those are necessary for what we're going to do. What we want to do is look at just this part. So if we are monthly at 6.5%, we have this. And we want to find an equivalent interest rate. So that's going to be R, compounded annually. So this is what we want to solve. Okay? So we're solving this for R. Well, this to the first power is just that. So I can just drop the parentheses there. So to get the R by itself, the first thing I want to do is subtract the 1 over and then we'd multiply by 100. And when I type this into my calculator, I would get that R is about 6 points, well, let's say 70, if I round this to 2 decimal places. Okay. The next topic is something similar and related, but slightly different. And it's called the annual percent yield. So through the previous examples, we've saw that, or this previous example, that time, that's our N, and the principal don't end up mattering because they're kind of the same for each of these accounts. So we can do a little bit of simplifying of this process and make a formula, or have a formula that can determine the equivalent annual compound interest rate. This is the APY, the annual percent yield, is just a simplified version of exactly what we did there. So if we look at what we have here, we have the 100, the minus 1, and then we have the 1 plus R over 100 times K to the K. So it's the exact same thing that we just did. So rather than going through that whole process, we can just use this much simplified formula. So it says, which savings account is a better investment? One that pays 7.8% compounded quarterly, or one that pays 7.65% compounded weekly? The way we can do that is convert both of those accounts to annual percent yields and see which one is better. So the quarterly one, the APY is 100 times 1 plus 7.8 over 100 times 4 to the 4th minus 1. And the monthly, the APY is 100 times 1 plus 7.65 over 100 times 52 to the 52 minus 1. So all I need to do now, actually let's call this APYQ and APYM to stand for quarterly and monthly, is to just go to my graphing calculator and type these in. So APYQ is about 8.03%, and my APY for M is about 7.94%. So which one would we want? Oops. We want the bigger one. So this is the better one. So my better investment is the 7.8% compounded quarterly. So that's a way to compare two different interest rate or bank account offerings based on their interest rates and their compounding periods. You can compare them and determine which one is best. The next thing we want to talk about is an annuity. And an annuity is important because in a practical sense, when people are saving for retirement or something, they're usually not just like dumping, like a huge amount of money, like $50,000 into their account all at once, and then just letting it sit there and do nothing to it till they need it later. Usually they're paying in little by little as they go. So this is a situation where an annuity is going to be a better description of kind of what's actually happening. So we define an annuity as an account in which a sequence of payments are made. An ordinary annuity is an annuity that always makes the same deposit at the end of each period, and that the interest rate is calculated on the account. The future value of an annuity consisting of n ordinary payments of R dollars at an interest rate per compounding period of I is given here. And note in this annuity formula that I is equal to R divided by 100K, and capital N is equal to Kn. So just like the compound interest formula, we just used these other symbols just to make it look a little bit cleaner, a little bit neater of a formula. So let's look at an example. It says at the end of each quarter, Sarah makes a $500 payment into an annuity account. If her investments earn 7.88 annual interest compounded quarterly, so again here we have K equals 4, here our R is 7.88, and our cap R is 500. What will the value of Sarah's annuity be in 20 years? So N equals 20. So we're looking for the future value because we want it in 500 years. So we said R is 500. So 1 plus, and then I is R over K, or 100K, excuse me. 7.88 over 100 times 4. And then cap N is K times N minus 1 all over 7.88 100 times 4. Okay. So now what's left is for us to type this into our calculator. I'm going to actually show you guys typing this in because this is kind of a monster. So I'm going to be very careful about applying my using my fraction commands. So I'm going to get a fraction here for the big fraction. I'm going to do alpha y equals, and then choose the n over d command. And then I'm going to have 1 plus, and then I need another fraction here for this little guy. So that's going to be alpha y equals, and then the n over d, 7.88 over 100 times 4. Move it outside the fraction, close my parenthesis, and then do to the 4 times 20 power, and then do my minus 1. Move down to the bottom here, and I need another fraction, so I'll do alpha y equals n over d, 7.88 over 100 times 4. And then I'll move my cursor outside of all the fractions and close my parenthesis. And press enter. So when I do that, I get that our future value is about $95,483.39. So not too shabby. And that was saving just $500 every quarter. right? So every 3 months, so it's like $120 a month or something, or $125. What is it? Well, I guess it's like a little less than $170 a month or something. And our last situation, we thought it was never going to end. It did. So the last situation is where we can talk about loans. And this is very important because most of us are going to end up having to borrow money at some point in our lives, either to buy a car or a house or some other big investment. And it's important to kind of be able to assess really how much you're paying for something. So we say the net or total amount of money borrowed for a loan is called the present value or principal value. The PV of a loan consisting of N equal payments of R dollars at an interest rate per compounding period of I is given by this formula here. And just like in the annuity formula, I is going to equal R over 100K and cap N is going to equal K times N. Okay. So let's look at a couple of examples here. So Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and the annual interest rate is 2.9%? So my present value is going to be the total value minus the down payment. So 18,500 minus 2,000, or 16,500. And we're looking for how much are the monthly payments. And the monthly payments were R. One minus, 1 plus, and then I was R over 100K. It's 2.9. And then in this case, K is just going to be 12 because we're talking about, monthly payments. So negative 12 times, and then N is 4. Okay, so to get R by itself then, we'll divide both sides by this fraction. And I'm not going to write it all down again because I have it right up there. I'm just going to write it in my calculator directly. I'm just going to write frac underneath it because I just didn't want to do it. So again, I'm going to be using this fraction command on my calculator to make sure that I get this right, because it's not easy to get this to come out right. You need it to look just like it does on your calculator. So I'm going to have the 16,500. I'm going to do a fraction command for this fraction. The numerator, I'm going to have 1 minus the parenthesis, 1 plus, and then I need the fraction command again for this fraction. That's 2.9 over 100 times 12. And then I'm going to close my parenthesis to the negative 12 times 4. And then I'm going to move down to the denominator. And I need another fraction here for this one. used alpha, y equals n over d 2.9 over 100 times 12. And if I press enter, I get $364 and about 49 cents. So using the same information from example 39 and assuming that all of Maria's payments are equal, how much interest does Maria pay over the life of her loan? Well, we know that we borrowed $16,500, right? That was our present value. And then we paid $364.49 per month for 4 years. So that tells me that we made 12 times 4 or 48 payments. So what we ended up paying then was 364.49 times 48. So our interest rate should be equal to, or the amount of interest paid should be the amount we paid for the car minus the amount we borrowed for the car. So if I do that on my calculator, I have 48 times this value here, so I'll just press second and then a negative sign to get that number, minus 16,500. So that we paid almost $1,000 in interest, $995.52-ish. So maybe you think twice about trying to buy that car on a loan, right? You end up paying an extra $1,000. But that's it. That wraps up section 15.5 as well as chapter 15 in totality. So at this point, you guys should be able to finish the homeworks for chapter 15. So that would be 139 through all the way to 184. Okay, bye-bye.